Welcome back, everybody. Oh, let me let some more people in. Oh, okay. All right. Hope everyone's doing okay. Let us continue with the chapter 4. We've been talking about the elements. We previously finished talking about the subatomic particles that we're going to talk about, which are the electron, the proton, and the neutron. Keeping in mind that the electron is a negative charge, proton is a positive charge, and the neutron obviously is neutral. Okay. The basic structure right now is that the nucleus, there's a nucleus in the atom in which the proton and the neutron exist. And then the electron at this time is just around the nucleus. Okay. We will find in the next chapter that that electron actually is in very specific energy levels. All right. So we got the element here. Now we have what's called an atomic notation. And that is the way how to means to express the element and give the following information. Give what's called the mass number and give what's called the atomic number. Now, every element has a very unique atomic number. There's 118 of them, each with their own atomic number. The mass number, however, can change. That changes with essentially the number of, not only the number of protons, but the number of neutrons. So by definition, down at the bottom here, you see that the mass number, keep in mind too, right now we're talking about whole numbers. Okay, the mass number, which is a whole number, is the sum of the number of protons and the number of neutrons. Now we talked about giving the proton and the neutron a AMU or atomic mass unit. Okay, we gave it a relative weight, which we assigned a value of 1 for a proton and 1 for a neutron. Okay, so the sum of the proton and the sum of the neutrons give you a whole number, which is labeled, given as the mass number. You guys be careful, okay? And it is written in the format shown up here where SY represents the symbol. And then superscript A, okay, superscript A left is the mass number. Right here, okay? And then subscript left, Z represents the atomic number, which is again found in on the periodic table. Now, the atomic number gives you 2 bits of information. One, it gives you the number of protons, okay, which is also equal to the number of electrons. Now, every element on the periodic table has what is called a net charge of 0. The protons have a positive charge, remember. The electrons have a negative charge. Positive, negative, you put one of each together, what happens? They cancel each other out and they have a net charge of 0. And so regardless if you have 1 proton, 1 electron, or 118 protons and 118 electrons, they all cancel out. And every element on the periodic table has a net charge of 0. We will learn here in the next chapter, chapter 2, that when we lose and gain electrons, we offset that equality of enough protons and electrons Now we end up with an actual charge of a negative or an actual charge of a positive. Okay. Remember this, if you lose electrons, you end up with a positive charge. You gain electrons, you end up with a negative charge. Okay. Almost like human nature, you become, you gain negativity, become more of a negative person, right? You lose negativity, you have more positive outlook in life. Maybe that'll help you out. Okay, so I'm going to share with you. I'm going to go back to the Canvas course because I want to refresh your memory on the simulation that we have for you. That will help you to understand the overall structure of an atom, okay, or at least with respect to our model. Now there is a module, which is the second module, named additional resources. Now in there's a variety of different additional resources. If you haven't had a chance, click on them and see what they're all about, because that will really help you throughout the semester. There's one called the Build an Atom. If you click it, it will send you to a site that has simulations. They have multiple simulations run by University of Colorado, I believe. The one I have here listed is called Build an Atom. Now, if we click, there's three choices, but just pick the first one, Build an Atom. You have this image here. You'll see three buckets, red, gray, and I guess bluish color. Okay, those represent the proton for the red, the neutron in the gray, and the blue color as the electron. Okay, hold on. Someone, I'm getting it. Here we go. Let me let them in. Okay, can everybody see the Build an Atom?
Yes.
Okay, good. Thank you. All right. And so let's go over, as you can see, we have a periodic table on the far right. Okay. Then click the plus, and that will give you a net charge scale. Then expand the mass number on the right side. Okay. Now, notice we have in the center an X. That's going to represent where the nucleus is. Then the other aspect to notice is we have this dotted circle, two of them. What those represent are shells or energy levels that electrons will exist. We're going to learn that electrons are not just thrown just anywhere in the atom, but they actually exist in specific energy levels, okay? So that's what the dotted lines represent. Now, if we grab a proton, you can just grab one and just drag it into the center X. It would put it anywhere around there, and it will automatically go to the center. And guess what you created? You created the hydrogen atom element, okay? All right, which has a positive charge, right? Which creates what we call an ion, because there's no corresponding negative charge. If you grab an electron and just bring it close to the model that we have and let go of it, guess where it goes? It went into the first circle, okay? And guess what happened? When I took it out, it became an ion because it has a positive net charge, okay? Look at the net charge. This is +1. But I balanced that +1 with the electron, and now I have a negative charge. Excuse me, a neutral charge. That is the element, okay? So we have one proton, one electron. Now note what, let me take the electron out for right now. Note what happens when I add a second proton. I create helium. And the third proton, I create lithium. I'm going across the periodic table. A fourth proton, beryllium. Next one, boron. I'm going right across the periodic table. And then I add 6 of them. I got 6 protons. And I now created carbon. So what does that tell you? Now, let me show you something. If I grab a neutron and I put them in there, I still have carbon. Notice that? It's still carbon. If I grab an electron and I put it in this model, I still have electrons. Excuse me, I still have carbon, right? And so the electron doesn't define the element, nor does a neutron define an element. What defines an element is the proton, okay? So putting in another proton, now that represents nitrogen. So protons define the element and what element it is. All right, so now I got carbon. I got a net charge of 6 plus 6. So I know the atomic number for carbon is 6. It means I got 6 protons. I must add 6 electrons. So I grab an electron, bring it on the outside energy level, and it goes into the inside level. Bring another electron, hey, it goes there too. It goes into innermost energy level. Notice my charge, my net charge now is a +4. So I grab another one, okay, bring it in the inner circle, but then boom, it goes to the outer circle there. Okay, so that implies something if you observe that the inner circle can only handle 2 electrons. So the only place that electron's got to go is to the next layer, which is on the outside. So now I still got a +3 charge, so now I continue to add electrons. And no matter how much I try to put it in the first energy level, it goes to the second one. And then one more. Okay. So if you look at your periodic table, you'll see that carbon is number 6. Carbon has 6 protons and 6 electrons, okay? And has a net charge here of 0 because I have equal number of protons and equal number of electrons. The other aspect you can see, there's a total of 6 electrons. 2 of those electrons went into innermost shell. The other 4, guess where they went? They went to the outermost shell. That outermost shell, and there's 7 of these shells, so we'll learn about that. But the one that contains the outermost electrons is called the valence electron. So let me very quickly go to the periodic table to demonstrate how the periodic table is very useful to give you a ton of information. Let's find carbon. Carbon is sitting, highlight it. Okay, there's carbon, number 6. Okay, 6 protons, 6 electrons. And we're going to learn here about the neutrons here in a second. You saw how it had 6 electrons and 2 of them were in the inner shell and then 4 were in the outer shell. Look at this Roman numeral in front of this column, Roman numeral 4. But that tells you that there are 4 electrons in the outermost shell. In fact, that is true for everybody in the same group, okay? And that's why they react very similar, because they share the number of the outermost electrons. And remember this is where all the action happens in chemistry, is in the outermost shell. Not going to happen on the inside where they're blocked from anything happening. It's on the outermost shell, okay? If I kicked in one more proton, one more electron, okay, that would be nitrogen. It will have 7 protons and 7 electrons. And if I had to guess how many of those 7 were in the outermost shell, what would you say? If I had to make an educated guess based on what I just told you, what would you say for nitrogen? I'm just talking about nitrogen right now. It has 7 electrons. Of those 7, 2 on their innermost shell, and the other 5 are where? On the outermost shell. And guess what group they're in? They're in group 5, Roman numeral 5. Okay? How many valence electrons do you think oxygen has? The neighbor next door. What would you say? What's that Roman numeral? VI. What number is that? 6. Okay. So oxygen has 6 valence electrons. It has a total of 8, but 6 of them are in the outermost shell. Come on, let me give you one more chance. Here's fluorine. It has 9 electrons total. How many of them are in the outermost shell?
7.
You got it. There you go. All right, now let's go the other direction. Give you a little something. You don't have to memorize this. It's just looking at the periodic table and where they're at. All right, let's take a look at magnesium, which is number 12 over here. Okay, it has 12 electrons. How many would you guess would be in the outermost shell?
2.
You got it. And, you know, in group number 1 electron. And that's important to know, because we're going to realize that nature has this thing about this magical 8 number. And when we were over here talking about the valence electrons for fluorine, it had 7. And it's going to strive to pick up one more electron. Okay? Because now it has 8. And for some reason, these elements, when they lose and gain electrons, their drive is to get 8 on the outermost shell. Okay? And that octet rule is what we call it. That is a driving force for a lot of chemical reactions, that one person is going to lose electrons and have 8 shells, 8 electrons around it, and somebody else is going to pick up an electron to have 8 around it. Okay, and that's why you see in blue there, and we're going to talk about that blue where you got aluminum +3, zinc +1, etc., etc. So that is what happens to these elements that gain electrons or lose them. They become ions. All right, let's go back to that. All right, let me clear this up. So now let's go back to hydrogen. Okay, and have 1 electron. Now, the mass number for hydrogen is 1 because it only has 1 proton there. Okay, the mass number here shown on the far right, bottom right. Neutrons come into play because they do a lot to stabilize the nucleus, okay, to stabilize this whole system. Because keep in mind, you got a positive and a negative, and you would think the positive proton will want to interact with the electron and pull it onto himself, but it doesn't. They stay apart. It's sort of like the forces of the planets around the sun. You know, we stay apart. We're drawn by the sun, but we have, as far as I know, we're not going to be going into the sun, attracted to the sun. Okay, and those forces are these nuclear forces, as are the gravitational forces, are amazing. If you think of how Halley's Comet, I think it comes around like every 70 some years. It goes around, orbits around that. My God, it's so far away and 70 some plus years away, but yet the force to bring it back in comes back. I always ask, why isn't it just drawn by something else out there? But it's not, it comes back. Also here with these forces between the nucleus and the neutrons and the protons and electrons, it's just amazing. A lot we don't know. Anyway, the neutrons come into play, so I can add a neutron, and I've increased my mass number to 2. Okay, because remember the AMU for the neutrons and protons are 1. Now keep in mind here, I added 1 neutron, and I still have hydrogen. I didn't change H; it's still hydrogen. I add a second one. I still have hydrogen. I can add an electron, and I still have hydrogen. Okay. I can add another electron, which would be a little more challenging to do that, but I still have hydrogen. The point is I can gain and lose electrons and neutrons all day, and I don't change what that species is. Now, The normal hydrogen that's out in nature does not have a neutron. Okay, but there are forms of hydrogen that do have a neutron, and one neutron and two neutrons. Okay, there are three types of hydrogens, each one being different by the fact that they have a different number of neutrons. Those are what we call isotopes. Okay, isotopes are just specifically that element with additional neutrons or less than additional neutrons, depending on the most abundant isotope that there is. Now, I'll give you an example here in a bit. Okay, because we all heard, I hope maybe you haven't, but you all heard of carbon-14 dating. Okay, there's 4 forms of carbon. We got carbon-11, carbon-12, carbon-13. And let's do that. Let's build carbon. I mean, demonstrate that. Okay, let's get enough atoms in there. We're going to be talking about carbon here in a bit, and we're going to visually see it. Okay, and so we're going to add the electrons now to have 6 protons, 6 neutrons. Let me get rid of all of the okay, so we have carbon. Oh. Okay, here we go. Notice up in the upper left, the number of protons, and then we're going to add number of electrons. So everybody's all evened up. We got carbon. This represents carbon 12 with 6 protons, 6 neutrons. This is the most abundant isotope or type of carbon in nature, about 98%. Okay, and we would write that. We would just say, let me clear this up here. Give me 1 second. We will write this as carbon -12, and that is the isotope of carbon. There is carbon -13. What that is carbon, but it has an extra neutron. And then we have a carbon 14, which means that has an extra neutron. Notice up on top, okay? All of these that I just wrote, carbon 12, carbon 13, carbon 14, and there is a carbon 11, which I want to pull it. There are 4 types of carbon out there. The only difference between the 4 of them is the number of neutrons. These are isotopes. The most abundant one here is carbon 14. That's what we find most of them in nature. Okay. All right. So keep that in mind. We'll come back to more information here in a second. All right. So let's go back to the PowerPoint slide. So do the simulation to help you out with respect to how the atom is put together, at least our current model. So atomic number equals number of protons, which is equal the number of electrons. The mass number, which is a whole number, remember that, a whole number is the number of protons plus the number of neutrons. Okay, and so every atom of an element has the same number of protons. Okay, so carbon always has 6 protons, always, no matter what form it is. You know, we have carbon dioxide. It's carbon that has 6 protons. Or we can have carbon a carbon who is situated in the form of maybe a fatty acid or a sugar. That is still carbon with 6 atoms, just in a different form. Okay. I've talked about atomic mass units. I said because of the masses, we use relative weights, and the proton and neutrons are all given an approximate atomic weight of 1 AMU. Whereas the electron is basically 0 because it is so tiny. Okay. Now, how do we calculate the neutrons? Well, two ways can happen here. One, I can write, well, oh, somebody's checking in here. Let's rearrange the equation where we got the mass number is equal to the number of protons plus the number of neutrons. Let's rearrange it to say that the neutrons is equal to the mass number minus the number of protons. Now we can get the number of protons from the periodic table just by looking up the element. Okay. This information directly from the periodic table and its atomic number. That's what that represents. The mass number is a little bit different. Okay. Because what we're trying to do is calculate how many neutrons we have in that element. But to calculate that, what we do is go to the periodic table, because the periodic table represents the most abundant isotope of all the isotopes for that particular element. Okay. Now, earlier I showed you, I'm just going to write it shorthand. I'm just going to say the symbol carbon 11, carbon 12, carbon 13, carbon 14. Now, if I was going to average these numbers out, 11, 12, 13, and 14, just average them up. We're going to add those numbers up, divide by 4. My average would be about 12 and a half, right? All right. Well, here's the thing. That is averaging those numbers as is, but every number here has a weighted average. So this one's like 98%. I'm thinking this one's about 1%. And this is much less than 1%. We got some numbers we can show you. But the point is this, just like your grade has a weighted percentage, the activities are worth a certain percentage, the exams are worth a certain percentage, they bring more contribution to your overall grade, certain of those assignments than others. The most abundant carbon in nature is carbon 12. It's about 98%. So now instead of averaging straightforward 11, 12, and 13, and 14, I have to account for that 98%. So I'm going to get more than 9 and 12 value into the overall average than I would within the 11, than I would than the 14 or the 13, right? And so the result is underneath the periodic table, on the periodic table, underneath the symbol for carbon, it has an atomic weight of carbon, which is equal to 12.01. Those have units. Right now, those are grams per mole. Don't worry about the units for now. We'll get to them. But be aware that's a ratio. We can utilize that. 12.1. And what that represents, it is the weighted average of all the isotopes of carbon, okay? And because carbon 12 is the most abundant, its number, the weighted average, is closer to 12, 12.01. So what that tells me is that I can go to the periodic table and at a glance, very quickly determine what is the most abundant isotope for any of these elements. For example, if I look at boron, number 5, okay? Look at its atomic weight. You see its atomic weight underneath the symbol? It says 10.81, all right? Round that number up to the nearest whole number and you get 11. What that tells you is that boron 11 is the most abundant isotope of all the isotopes of boron. And that is the mass number. So I can take 11, subtract the number of protons, and that gives me the number of neutrons, which would be 6, right? And so let me draw here. So by rounding at that 10.8, now I can write boron hyphen 11 is the most abundant. And so 11 minus 5 equals 6, and that is the number of neutrons for boron 11, which is that one right there. Because 5 plus 6 gives me 11, okay? I can do that for sulfur. Sulfur, the most abundant isotope of sulfur, guess what? Will be sulfur 32. I take 32.07, round that 32.07 to the nearest whole number, and that is 32. Okay, 32 minus 16. How many neutrons do you think that sulfur 32 has? 16. Who can tell me the most abundant isotope for chlorine? Give me what we just talked about.
35.
You got it. And how many neutrons would it have?
18.
18. You got it. Exactly. So the most abundant isotope is chlorine 35. Take that 35, subtract 17, you got 18. So chlorine 35 has 17 protons, 17 electrons, and 18 neutrons. Here's that carbon I talked to you about. Yes, there's 4 types of carbon: carbon 11, carbon 12, carbon 13, carbon 14. But because the atomic weight is closer to 12, around 12.01, carbon 12 is the most abundant isotope. Therefore, I have 6 protons, 6 electrons, 6 neutrons. Okay. Now, sometimes they will give you the mass number right away. And because the way they do that is this. I'll show you that. Let's go back. They may say, carbon 13, write it out. Well, they're telling you the mass number there. They're talking about carbon 13. You don't have to go to the periodic table to determine which one you're talking about. If they don't give you this information, then you can assume they're talking about the most abundant isotope, and you just go straight to the periodic table. Otherwise, they have to give you this information before you can calculate how many neutrons there are. But if you see it's carbon 13, carbon still will have 6 protons. It will have 6 electrons, okay? And therefore, being carbon 13, how many neutrons do you think it would have? For carbon 13.
7.
You got it. Exactly. Okay. Now you get it, you get the gist of it. All right. So let's go on and see if we can figure it out. So here we go. Okay, we'll come back to it in a second. But 2 things here. They're telling you just write the atomic notation for potassium 40. All right. Where did it go? Okay, that is the atomic notation. SY is the symbol. The mass number is upper left, atomic number bottom right. Okay. So they're saying potassium 40. Now, is potassium 40 the most abundant isotope there is? What do you need to do? I need my periodic table, right? I go on my periodic table, find out the potassium has a mass of what, 39.1. So no, potassium 39 is the most abundant isotope. Okay, and so they're telling you the mass number here, and so you simply got to just take that 40, put it up in a superscript left, and 19 is the number for potassium. Okay, the most abundant isotope would be potassium 39. They both have the same atomic number, of course. Otherwise, if they did not have the same number, there'd be different elements. But they're going to differ in the mass number because they differ in the number of protons. Okay, and then to figure out simply how many neutrons you have, you just simply subtract 40 minus 19, and you get 21. Okay, for potassium 40, how many neutrons would potassium 39 have?
$20.
You got it. Exactly. Now 39 minus 19 gives you 20. You see, so the difference here is just simply the number of neutrons. And technically, everybody, even though the most abundant isotope, we call it the element, it's still an isotope, and some elements have 2 or 3 isotopes, some have a lot more. Okay. And they happen in nature, and they're around us. Obviously, some of these we actually make, but okay. All right, another example here. They're asking you write the atomic notation for bromine 81. All right, so when we do that, we go look up the atomic number for bromine on the periodic table, and that's number 35, element 35. So it's subscript left, so the 35, and then they give you the mass number, and that's 81. And that simply, the next question is, well, how many neutrons? Okay, that's 46. So but bromine 81 has 35 protons, 35 electrons, and 46 neutrons. Okay, 46 neutrons. All right, this is what I just spoke about with the different isotopes. You got carbon 12, carbon 13, carbon 14. All of them have, carbon 11 is missing, but all of them have 6 protons, okay? All of them are carbon. They differ only in the number of neutrons, which they have in this case 6, 7, and 8 respectively for the different carbons. Carbon 14 is the one that you may be familiar with. We do, date carbon dating. Those are the isotopes that are utilized. Okay. You may see a table like this. Okay. Now they're saying oxygen 16, oxygen 17, oxygen 18. Everybody's oxygen. So they're going to have the same number of protons and the same number of neutrons. The mass number is given there. You don't have to look anything up. It's right there. Mass number 16, 17, and 18 respectively. Okay. And then the rest is calculating neutrons. It's simply subtracting the mass number from the number of protons. Okay. So we got 8 plus 8 gives you 16, 8 plus 9 gives you 17, and 8 plus 10 gives you 18. Okay. So all of them isotopes, they only differ in the name and the number of neutrons. All right. Now, this is an explanation as to why our atomic weights are decimal numbers. The numbers underneath the symbol, those are decimal numbers, because they are the weighted average of these whole numbers, which brings me to a point. Whenever you're using the atomic weights or the periodic table, they would not be used to determine your significant digits, your sig figs. And why is that? Because these are averages of whole numbers. And averages of whole numbers give you an infinite number of significant digits. So that's point number one. And point number two is when you use the atomic weights, please use the atomic weights in the periodic table that we utilize. Yes, you can look them up on the Google and you'll have different numbers, but the answers used that for calculations utilizing the atomic weights are based on the atomic weights of our periodic table in Canvas. And if you use one that might be slightly different, Canvas is not AI and cannot pick that difference up, and it will count it as wrong, even if you're off by 1 decimal point. Okay, so use our periodic table atomic weights. All right. So like I stated, we can use the periodic table and determine the most abundant isotope based on simply by rounding up the atomic weights. And again, you can see that carbon 12 represents almost 99% of the carbon out there. And so, of course, it's going to have a higher weight in the average, and therefore its number would be closer to 12. Now, using the periodic table, which one do you think is the most abundant isotope here? Lithium-7 or lithium-6? Excuse me.
Is it lithium-7?
Lithium-7. Well, let's verify. Let's go to the periodic table. Okay. We got to find lithium, which is element number 3. Let me highlight it for you, which is right here in yellow. Okay. Its atomic weight is 6.94. Round that up, you get lithium-7. Okay. And so we go back, and there's one of our choices. Yes, it is. So lithium-7 is the most abundant isotope. Okay. Chlorine-35, chlorine-37, similar scenario. You go through the periodic table, round up its atomic weight. You'll see that chlorine, rounding that number up, is 35.45. It is chlorine-35. Okay. So that's how you determine the most abundant isotope based on the atomic weights given to you from the periodic table. All right. A lot of the isotopes that we work with, or that we have, at least that we know of, are very radioactive, extremely radioactive. And so, for example, curium, which is element number 96, has its atomic weight in parentheses. What that tells you, that's very unstable. Okay. And being unstable, it's difficult to calculate, be able to figure out all the isotopes out there. This element number 96 was named after Madame Curie. Just a quick side note question, FYI. Does anybody by chance know where Madame Curie was originally from? Very famous scientist. She had 2 Nobel Prizes. And her children also won some Nobel Prizes, along with their husband.
She was Polish, wasn't she?
You are 100% correct. She was Polish, and the reason she went to France was because, and I tell this to my daughter, is because in Poland during the time period, women were not really expected to go on to college and get a higher degree or any type of education. So she ended up in France and got her doctorate. Her doctorate probably is the only doctorate that was, when you get a doctorate at the end, when you do what's called a defense, that means you go up in front of people, normally just your maybe 10 people or so Irish, 5 to 10 people, and you defend it. You spend all this time working on your doctorate and you defend it and ask questions, and you should be the expert there. Anyway, Madame Curie's defense brought a lot of scientists from around the world. It was just a loaded pack thing. Very impressive doctorate defense. She did a lot. Okay, and she was a chemist by background. Let's clear this up. All right, so we're going to stop with the atomic weights, the formulas for the elements for right now. We're going to get into talking about chemical formulas. Okay, not specifically, but basically just looking at a formula and just be able to tell how many elements of each are in that formula. Okay, because the elements in there tell us the letters and the symbols tell us which element, and then The subscripts tell us how many of those elements, okay? They're not going to tell us much about the way things are bonded. And if, for example, there's no subscript, like in mathematics, normally if you got an equation or some sort, you have for a letter or even algebra, you don't have a number in front. It's assumed to be a value of 1. Okay, it's unwritten. For example, H2O, that tells us that the subscript tells us that there are 2 elements of hydrogen and 1 of oxygen. Notice there's no 1 on the O, it's just understood to be a 1. Okay. And if we take a look at this formula, we're not concerned about what it is. If you were doing organic chemistry, you certainly will be wondering what that thing is. But here, what we do is just simply want to count up the number of atoms. So in this case, we have 3 carbons, 6 hydrogens, and 3 oxygens, giving us a grand total of 12 atoms. Okay. Now, here's something interesting here. We have a parentheses. And that gives us some special information here. See this parentheses here, when you see that parentheses, anything within the parentheses is treated as a unit. It's a packet of what we call polyatomic ions. We don't separate them. They come together as a packet as such. So this polyatomic ion has a formula NH4. If we need to add more, which we're going to learn that sometimes we do, we need to add more, we put a parenthesis in the subscript. So that tells us that we have 2 nitrogens and a total of 8 hydrogens within that parenthesis, okay? And then we have the C for carbon, 1 carbon, and 3 oxygens. So we have a grand total 14 atoms. 2 nitrogens, 8 hydrogens, 1 carbon, and 3 oxygens. Now, why do we want to know this? We're going to eventually be able to look at a formula and break it down into the percent composition of each element. So we'll be able to calculate what percentage nitrogen is, what percentage hydrogen is, and what percentage carbon, and et cetera. But we have to identify, to be able to do that correctly, we have to identify how many of each atom we have in that formula. That, by the way, that formula is called ammonium carbonate. I was going to introduce you to some names. Okay, let's take a look at these. The first is H3PO4. I know you're not aware of this, what it is, and that's okay, not right now, but you should know this. If you drink soda pop a lot, you're drinking a lot of this. This is AKA phosphoric acid, okay? Phosphoric acid contains 3 hydrogens, 1 phosphorus, and 4 oxygens. Okay. The next one, Ca, which is calcium, and then in parentheses you have an OH moiety. OH, it has a very specific name, but there's 2 of them with that subscript. So we have 1 calcium, 2 oxygens, and 2 hydrogens, AKA plus calcium hydroxide. Put these down. And finally, the last one, we have aluminum, Al, good old L, aluminum, and there's 2 of those. So we got 2 aluminums, and then we got a parentheses, and so we got 3 of these SO4 groups, 3 sulfurs, and 12 oxygens. So we have a total of 17 atoms, 2 aluminums, 3 sulfurs, and 12 oxygens. Okay? Now those things in parentheses, those are what we call polyatomic ions, and I'm just going to introduce them to you now because we will be using them quite a bit. And if you look at the infamous periodic table, now you know we do a lot of referring to it. You'll see in the table, in the bottom left, there's a table called polyatomic ions. There's the OH we just talked about. That's a hydroxide, and it's good to be familiar with this because these guys, they come together as a packet. We don't change them. they have their own unique name, okay? Here's the other one called carbonate, and we just did. And then this one you might be familiar with. This is the formula for something you put in your chocolate chip cookies. Bicarb or hydrogen carbonate. Why would we put that? Just a question. Why would you put that in your chocolate chip cookies or cookies in general? Because part of the recipe calls for that. Why would you add that? What's the function of that? Anybody know? Lost you. Where you go?
To make them fluff up or stabilize somewhere.
Right. Your first question was correct. Your first answer, excuse me. I asked the question, sorry. Because the sodium bicarb, when you heat it, breaks down. It decomposes, okay? And when it decomposes, one of the products is carbon dioxide. And carbon dioxide makes your cookies rise. Same reasoning you put bugs in your bread to cook it, right? Why? Bugs, you know, I'm talking about yeast. But why would you put yeast? Well, similar reason. The yeast are a living organism, okay? They start to break down the sugars of your material. One of the byproducts, like wheat, is carbon dioxide, and that causes your bread to rise, okay? Without that, you got matzah, unleavened bread. Didn't have time to get it to rise. So anyway, periodic table, polyatomic ions. And let's go back to 17 atoms. And like I said, we're going to learn how to do these percent calculations because we know that doing these calculations that for water, for example, will consist of 11.2% hydrogen and 88.8% oxygen. And that's water, whether you find it here in Arizona or some asteroid someplace. H2O has the same configuration, the same amount of that element. All right. Okay, guess what? Congratulations, you are done with chapter 4. Okay, and any questions about that? Okay. Which brings us to chapter 5. Now, earlier you recall that we were talking about the structure of the atom, and we had good old JJ and Rutherford, and they finally came up with the model that we had a nucleus, and Rutherford was responsible for the neutron, the proton in the nucleus. And then Chadwick came along and discovered the neutron, and then JJ discovered the electron, J.J. Thomson. And so at this time, we had this model. We got the electron someplace in the atom. We're not quite sure what's going on here. And then we got the nucleus. That's about all we know. Well, it continued. The model was being developed even further, okay? And earlier, I also stated that the mass of an electron is so small, we basically treat it as a zero mass. Okay, keep in mind that it's not really zero, but it's close enough, approximately zero. And with that mass so small, it has behavior like light. It has properties of light in the way light behaves. And so what I need to do is to kind of talk a little bit about light and properties of light, okay? All right, and what we know about light. Okay, so how do we represent light, or what we call electromagnetic radiation? That sounds like a bad name, radiation. We think of X-rays. Well, X-rays is only part of it. When we talk about electromagnetic radiation, we're talking about a series of energy. We got radio waves that are not very high in energy, and then on one end, and the other end, we have gamma rays or X-rays that are very powerful, okay? And light itself can be very powerful. We have lasers that can cut metal, and very, very strong. Okay, so how do we look at light? Light can be looked at as this wave that we got going on here, okay? Now, if we were to take this wave, and if we were to mark a spot, say on top of the hill, because the wave is kind of represented by hill and a valley, hill and valley, hill and valley. If we mark a spot on top of the hill and then mark another spot on the next hill, that distance is what we call a wavelength. This is a measurable quantity that we can actually give a number to. It is a specific wavelength. Now, we're on top of the hill, but we can do the same thing by going bottom of the hill, if you will. And that distance is that same distance up there. Or if we pick a spot downhill and we pick the same spot downhill on the next wave, again, that distance is the same wavelength, okay? A very specific number. Now, that symbol is called lambda, and that is the distance between peaks and adjacent waves. Now, the frequency, you might be familiar with the frequency because, if you went out recently and bought a computer, you probably were asked, I want a fast processor operating at maybe 2 or 3 gigahertz. That is the frequency. The frequency could be thought of as something that happens within a given time period. The number of times it happens within a time period, normally within one second. So if you do something in 1 second, you get a frequency of one thing per second or 1 hertz. If I do 1 billion of these in 1 second, then I got 1 gigahertz. Okay, hertz is the unit for frequency. Okay, so the frequency is the number of wave cycles that are completed in a second. Okay. All right. So if we look at these 2 diagrams, obviously represents 2 different wavelengths. You can see the top one relative to the bottom one. The top one has a longer wavelength than the bottom. Okay. And if we were to say this is 1 second from this point to this point was 1 second, you can see that in that time period that we got maybe 2 wavelengths in the top image occurred, where the bottom we got 1, 2, 3, 4. So 2 wavelengths versus a 1 wavelength versus 4. Okay, and that is the frequency. So obviously the bottom one has a higher frequency because more of those waves pass through in 1 second time period, compared to the upper one that has a lower frequency, okay? Now, associated with the frequency is energy. So if you have a low frequency, you will have a low energy light, but a long wavelength. Long wavelength, low energy, low frequency. An example would be radio waves. So radio waves are wavelengths are in meters long, very long. Same radio waves, you turn your radio on, listen to the music, okay, or whatever you listen to. Not high in energy, not known to cause any type of physical problems, okay. Down at the bottom, you have a short wavelength, which is associated with it a high frequency. Okay, and a high energy. An example of this would be an X-ray. An X-ray has a high frequency, and a short wavelength, and a very high energy output. High enough, X-rays will go right through you and cause all kinds of problems, tissue damage, and so forth. All right, so that's the difference between long wavelengths and short wavelengths. Wavelength goes down, frequency goes up, energy goes up, and vice versa. All right, so B and A represent a high energy, and low frequency is represented by A. This is the spectrum, and it's not the scale. Okay, it's a little bit exaggerated. If you look at the far right, you have radio waves, or very big waves in meters, and then the far left, you have gamma rays. You find a lot of those out in space. Very powerful, very deadly, high energy, very deadly. This is kind of out of perspective, but the visible wavelength is extremely small. Our eyes have a very small spectrum of light that we can detect in the visible. Infrared's right here, ultraviolet, a little bit more energy, microwaves, much less energy. Okay. And we have instrumentation that can pick up on these, but we can't see. All right, be familiar with the type of wavelengths that we're dealing with, from gamma, X-ray in the order that you see here, okay? That may be of importance down the road. All right. Back when we were talking about J.J. Thomson and Rutherford and so forth, 1900s, remember that? Okay. And I mentioned at the time that we were dealing with other scientists that were doing some pretty remarkable things, not along with Einstein, but there were other ones. 1900, scientist by the name of Max Planck, very famous scientist. There's an institute in Europe named after him, named the Max Planck Institute. He proposed a very unconventional idea for the time. He proposed that energy was emitted in small bundles, or what you call quanta, small bundles of light. Okay. And hold on 1 second, something going on. There we go. So his idea was that energy was not a continuous process. It was emitted in specific quantities of energy, or quanta, okay? And he defined that every individual unit of light he called it a photon. Hence, your sci-fi fans, photon torpedo, that makes sense now. All right, so he proposed the energy exists in levels and was not continuous, and therefore are quantized. Quantized means very specific energy levels. And to look at it, maybe using this diagram where you can see the wedge and the balls represent the energy, that would be in a continuous stream of energy. But he said, no, that's not the case. Energy is more like the stair steps, where every level is a specific amount of energy. And you'll be surprised that we will talk about how we learn this, okay, by the emissions of light from the elements and the emission of light that was broken up into the different wavelengths. All right, so here comes 1913, same time period, okay, along with JJ and Max Planck and Einstein and so forth. And here comes Niels Bohr. He proposed that electrons orbit around the nucleus. I think that idea was around, he just didn't know how exactly. But he went further and said that these electrons of the elements exist in very distinct energy levels. And if we look at the periodic table, FYI, I know yours isn't marked, but you may want to take yours and mark it. I got a mark here in the far left with numbers 1, 2, 3, 4, 5, 6, 7. Okay, those represent the one second. If I start at hydrogen, go all the way across to helium, that's level 1. Okay, if I start at lithium, go all the way across to neon, that's level 2. Sodium all the way across, argon level 3, all the way down to level 7. Okay. All right. So there are 7 energy levels which are denoted here on the periodic table. We call those horizontal periods. Okay. The Roman numeral numbers that we talked about earlier, as far as valence electrons, we call those groups. Okay. So the periods represent a specific energy level. And we're going to learn that within those groups, within that energy level, there are sub-energy levels. And electrons exist in sub-energy levels that, let me clear this up, that are noted as orbits or orbitals. Okay. Electrons are quantized and they exist in distinct energy levels as proposed by Niels Bohr. And as I stated, 7 energy levels, which is quite fascinating because the periodic table as we see it now wasn't quite like that then. And so it kind of like, wow, it kind of fell into place, the elements. Right now, we are 7 energy levels we have created, we have made up or have identified up to 118. Guess what? When we come up, start making the 119, we're going to have 8 energy levels. At least that's the theory. Okay. All right. Now, each orbit or each energy level has a specific radius and energy, and from a distance of the nucleus. Okay. And so that's why in that simulation you saw that dotted circle, because that represented the energy levels. Okay. And here in this diagram, it just shows 7 of them. Excuse me, 3 of them, but there are 7 of them, right? 3 of them are shown. And you already learned from the simulation, remember when I was pushing the electrons, that very first one only handled 2. Okay? Only handled 2. That's interesting. We're going to be able to use the periodic table to show that. Because if you go to the first period, it goes from hydrogen to helium. Helium is number 2. That's it, 2 electrons. And you're going to move to the next energy level. All right. Now, how do we know this? How was this determined? This was determined by what are called line spectra. Now, I'll go over the slide, then we'll call it a day. Okay. What was done is these elements and compounds were placed in a sealed tube, just like fluorescent bulbs. Energy was hit, they hit it with electrical circuit current and excites the molecules. Okay. Bear in mind, the tube was filled, it was put in a vacuum with that material, whatever the material is, and then a current was passed through that tube. The molecules inside are going to pick up on that energy, okay? The molecules get excited, or the elements get excited. They go up into what's called an excited state. You start off in the ground state. When you turn off the fluorescent bulb, there's no light. Everybody's in the ground state. You turn on the fluorescent light, flip the switch, electricity kicks in. The gas molecules in there get excited, okay? But they don't hang up there for very long. They can't. They drop back down. Mother Nature being Mother Nature. So when they drop back down, they must release the same amount of energy that they picked up. And they release it as light and heat, okay? Now, if we take that light that's emitted and we run it through a spectrum, prism actually, we will collect what's called an emission line spectrum, sort of like this setup. You get the tube, you run it through slits, and that's just to focus the light. And you run it through a prism. We know what a prism does, right? If you don't know, you ever seen a rainbow? Then you've seen the prism in action, okay? A rainbow does that. It breaks that light up into the different wavelengths of light so you can see the different colors. At least the ones we can see, they're visible, okay? And so it breaks it up, and guess what? You get this line spectrum. This is an example of the line spectrum of hydrogen gas, okay? Very distinct lines, which when you run through the calculations and so forth, can assign to them a specific wavelength. That wavelength is NM, called nanometers. So you can see the first one, the violet color is at 410 nanometers, the blue violet 434, so on and so forth. And the distance between them is a specific amount of energy, because you can calculate now from that wavelength an amount of energy, and just determine that these electrons that were in helium, there's different energy levels, okay? And it's very distinct. The other awesome thing about this is that that's the fingerprint. That is how we know that, by analyzing the light from someplace, that we got hydrogen there, by looking at its light spectrum. Now, if you do that to a variety of different compounds and elements, see here, lithium, sodium, potassium, so on, they all have their own emission line, their own unique color, their own unique wavelengths, which then could be assigned to the electrons that they have and figure out the energy levels. From that information, we're going to take that. We're not going to work on the actual calculations. No, we're going to talk about how these electrons are not only in a specific energy level, but they are in what we call an orbit, or a sub energy level called an orbit, and they exist in that particular orbit. And there's different types, only 4 types, but we're going to learn about those. Okay, well, tell you what, let me stop it here. We're going to stop it here on